All right, let's talk about Gauss-Markov theorem. So this is a good one. This is a big one in statistics, and we're going to prove it in parts. And so what the Gauss-Markov theorem says is that the least squares estimator is the best linear unbiased estimator. This is often abbreviated as BLUE. And so what does this mean? So by best, it means that it has the smallest variance. Among linear, and so by linear, it means that it's linear in the observed output variables. And we know this is true. We don't really need to prove this. This is just based on kind of the facts of how we're doing this estimation. We do need to prove the best part, and we're going to get to that soon. It's unbiased, and so we can also prove that this is an unbiased estimator. And then finally, it's an estimator. And so the fact that it's an estimator basically means that it's using some sample data to estimate some prediction, which we know is true as well. So we're going to basically take the linear and the estimator part of this to be true, and we're going to prove the best and the unbiased part of this. So Gauss-Markov theorem says that least squares is the best linear unbiased estimator. And so let's show first that it's unbiased. Okay. So what do we want to show? Well, we want to show that the expectation of beta hat is equal to beta. And so what is beta hat? Well, we've spent quite some time deriving that. That's basically most of what we've done in this class so far is deriving this beta hat and the subsequent hat matrix that goes with it. And so beta hat is equal to x transpose x inverse x transpose y. I think this hopefully will be something that just is intuitive to you over time since you've been seeing it so much. Eventually this will just sort of be something easy to regurgitate. You'll just kind of know when you hear beta hat, it's x transpose x inverse x transpose y. Okay, and let's remind ourselves what y is. Well, y is equal to x beta plus epsilon. So we can actually plug that into this equation. So we know that beta hat is x transpose x inverse x transpose y, and we can substitute x beta plus epsilon in for y here. And so what I want you to do is simplify this expression. So I basically want you to pull through this expression to simplify it so that we can then take the expectation to see if it's truly unbiased. So I'll give you a little bit of time to do that. All right, so let's simplify this expression. So I'm going to pull through this x transpose x inverse x transpose. I'm going to pull it through with this x beta and then also multiply it by epsilon. And so when you take x transpose x inverse and multiply it by x transpose x, that ends up just being the identity matrix because you're multiplying the inverse of something times the thing itself. So then we just end up with the identity matrix times beta plus, and then this last part, x transpose x inverse x transpose epsilon is going to stay. Okay, so we've simplified this expression. Now let's take the expectation. And so the first thing we're going to do is actually take the expectation of beta hat given x. And the reason why this is helpful is because We actually know that the expectation of epsilon given x is 0. This is an assumption of least squares, and we're going to use this fact in trying to calculate the expectation of beta hat given x. And so this is what we're calculating here, the expectation of beta hat given x, or the expectation of the identity matrix times beta plus x transpose x inverse x transpose times epsilon given x. And so what I want you to do is I want you to try this. I want you to use the information that we talked about in the previous lecture and solve this expectation. And then type your answer in a .rmd file and submit the .html file on Canvas. And so this is going to be the application exercise for today. And remember that the whole point of this is to try this yourself. But if you get stuck or don't get it, just turn in what you have. We're going to go over it in the next class. But the point is sort of to give you a chance to try it yourself. One thing I'll mention is that might help with this is when you pull this expectation through, if you're taking the expectation of x given x, then x becomes a constant and you can just pull it out. So that's kind of a little fun fact that will be helpful. And also, of course, remember this assumption that the expectation of epsilon given x is going to be 0. Okay, so go ahead and try that. I'm going to give you a little spoiler alert. You're going to end up getting beta if you do it correctly. The expectation of beta hat given x is beta. And so the thing we actually want to know is not the expectation of beta hat given x. We want to know the expectation of beta hat. We want to make sure that that thing is beta to make sure this is unbiased. And so this is where the law of iterated expectation comes in that we just talked about. And so we know from the law of iterated expectation that the expectation with respect to x of the expectation of beta hat given x is going to be equal to the expectation of beta hat. And so let's use this piece of information and we'll use what we just calculated, what you calculated for your application exercise to be able to get to this expectation of beta hat. So the expectation of beta hat given x is beta, so I'm going to plug that in for this. So I end up with the expectation with respect to x of beta. Now the expectation with respect to x of beta is just going to be beta. And now we can just pull that now to be the expectation of beta hat, since we know that due to the law of iterated expectation, the expectation of x given this conditional expectation is going to be equal to the expectation of beta hat. And so now we've shown that the expectation of beta hat is equal to beta. And so we've proved our unbiasedness. So Gauss-Markov theorem, this says that the least squares estimator is the best linear unbiased estimator, or BLUE. And again, this means best, smallest variance, linear in the observed outputs, unbiased, which we just proved that it's unbiased when estimating beta and that it is an estimator. So in the next class, we're going to show the best part. We're going to prove that part of the Gauss-Markov theorem. But so far we've proved, we've demonstrated these last 3 parts, and so we're on our way to proving the Gauss-Markov theorem.